I'm here to introduce you to using R. And there's no way that in 3 hours I could teach you to speak French. And so you can't similarly learn a whole language in 3 hours. But what we're hoping for is basically to give you some tools to at least know the basics and have a sense for how to get your own answers, how to start to think about finding information. How do I do this in R is something, I Google things to that effect 20 times a day. All I do is Google how to do things in R. And there's going to be a lot of that. And that's how the learning process works. Like I said, it's a language. You can't pick it all up in 3 hours, but we're hopeful that you can sort of get to a point where you're comfortable Googling error messages or reading help documentation and just sort of answering your own questions and then deciding for yourself when you need to then reach out to other people for help. So I have been coding in R since 2012, so 11 years. And, I've picked up a lot of stuff, but a lot of it's just like random stuff that you pick up from Googling. There's not a ton of coherent, lessons that I can teach. So the introductory stuff is really, I think, the basics of R. These are the fundamentals that can be built upon. And then 90% of everything else is just Googling. And so we're going to get you that first 10%, hopefully. So I'm going to jump in, and unfortunately, I'm going to be jumping between two different sets of slides today. So both of these sets of materials are available online. They're all open source, so you don't have to worry if you miss something on the slides. You can find them online. But I'm actually going to start with some slides from Chris Pachorik at UC Berkeley, who is the person who taught me R. And so I'm doing the best that I think I can in terms of finding the best materials and teaching you the way that I learned it. There is a little bit of a sense in a lot of statistics circles that we shouldn't be teaching base R, we should be teaching tidyverse. And tidyverse is sort of a dialect within R. It's got a lot of very unique syntax and very unique usages that you don't see anywhere else. And for some reason, a lot of people in statistics have decided that it's easier. And so when they teach non-statisticians how to use R, they teach tidyverse on the assumption that it's easier. I don't think it's easier. And, I think it's a little weird to use one thing but teach another because you think it's easier. And so I'm teaching you the things that I think are most useful and have genuinely helped me in my, academic career. So we're going to get a little bit of tidyverse, we're going to get a little bit of base R, and we're going to sort of mix them together. And I'll try to highlight the strengths of each, because it is sort of a Bayesian versus frequentist thing. If you're familiar with the sort of two camps of statisticians, there are things that both excel at. And so you can easily have both in your tool belt and thereby do a lot of different things. But to start things off, I'm going to start in base R, which is this. So this is RStudio. And we asked you to all have RStudio installed before this bootcamp. And a lot of waiting for people. So hopefully you got it installed. I apologize for the Zoom thing over here. It's going to be hard to see part of the screen at all times. Yeah. Anyway, this is RStudio. RStudio is the program, the interactive environment from which most people choose to write their R code. So RStudio is not R the language. R the language is hosted by CRAN, the Comprehensive R Archive Network. This is where you would go to download R. So when you want to update your R installation, you would go to the CRAN website. You can see that I've used this link recently. So 4.3.1 is the most recent edition of R. They're all named after deep cuts, like references to Charlie Brown. I don't know why. Somebody along the way really liked Charlie Brown. And then RStudio is a separate application that you can download from the company formerly known as RStudio, now called Posit. But I just do the RStudio desktop version, which is free for academic use and typically free for most like private use as well. You have to be a really big company before RStudio comes and shakes you down for money. But this is how you install RStudio if you haven't already. But I would strongly encourage you to do that so that we can sort of follow along in RStudio as we go. I'm going to try to make this bigger, so hopefully you can see. There we go. Enhance. And so right now, all I've got is basically this one big window on the left here that is my console. And then I've got another window for plots over here, but I haven't made any plots yet. And the typical way that I like to work is with an R script. And so if I just open a new R script, that's going to open a new window above the console. And this is where I can write all of my R code without it being run. Where it gets run is in the console. And so we'll see some demonstrations of that in just a minute. I want to get started talking about the actual language of R, though. So one of the most basic things that you can do in R, that you can do in pretty much any programming language, is treat it like a calculator, right? So these slides are going to have a little bit, it's a little bit hard to read, but whenever you see things on two lines like this, the non-indented one, this is actual R code, right? And then the two octothorpes, the 2 pound signs, this is the output. So if you put 2 + 2 into an R console and hit enter, it'll return 4. The little 1 next to it just means that this is the first part of that output. So if there were multiple parts of the output, you might have more numbers. But we can just go ahead and see what that looks like over here. I type 2 + 2 into the console, it says 4. Not surprising. And there are some built-in constants like pi. You can use functions. So RUnif is a function that produces a random uniform number, R for random, unif for uniform. Square root function, log function, and some other sort of more esoteric comp sci style mathematical operations. There's also scientific notation, but basically this is the most straightforward way to use R. Honestly, anytime that I need a calculator in my daily life, I've always got RStudio open. So I always just go over to RStudio and like, hey, what's 47 + 27? I don't know. I'll just go over to R. With that sort of foundation, I'm going to point out some of the functionality of RStudio, because I think this is how you really get good at using R. You should spend as little time as possible actually writing code. This is my sort of philosophy here. So if I've got code up here, 2 + 2, 2 times the cosine of 17. This is basically just a text document. It's a plain text document. Nothing special happens until you run it in the console below. And so this time I'm copy pasting and it runs when I hit enter. But if you want to do it quickly, you can just put your cursor on that line and hit Command Enter on a Mac or Control Enter on Windows, and it'll run that line of code in the console below without moving the cursor down. And this is a very quick way to run lines of code that you have written if you need to test them without copy pasting, switching back and forth. There's one other thing. Oh, and similarly, it's often the case that you'll want to rerun previous lines of code or very similar previous lines of code with minor tweaks. If you go down to the console and hit the up arrow, it'll pull up all of the most recently run code. Sorry. Oh, there's some from my actual work. But basically, if you hit the up arrow, it'll let you cycle through all of the lines of code that you've run recently. These are things that are very helpful when you're trying to be quick. Okay. I'm going to skip over this, except to point out that there's this sort of trick question down here. Cosine is not a built-in function. I don't know how they would expect you to know that at this point. Cos is the built-in function, and square brackets are not the same as parentheses. So the ones with the square brackets don't work. X is not a multiplier. You need the asterisks if you want to do multiplication. And there is no implicit multiplication, so 2 pi is not a valid syntax. If you do this, you'll get something weird because you have an open parenthesis that never gets closed. It gives you a little plus sign down there, and that says R hasn't detected the end of a line. It thinks you're still going. And so I could just keep going forever until I add that closing parenthesis. Okay. Now we get into the fun stuff, right? All of that is very basic, stuff you could do on a $2 calculator. But storing values is when you start to get into the actual sort of crux of coding. So the way that you store a value or assign a value is with this assignment operator, which is a less than and a hyphen. When I read code like this, I'm going to say val gets 3. And that's not official or anything. That's just how I read it. And so if you hear me say something weird like val gets 3, know that by gets, I mean this less than minus construction, which is the assignment arrow, the assignment operator. And so what this does is it creates a variable. I'm going to execute that line of code, and it ran. And now if I open up this environment tab, if I give it a little bit more space, we can see under values, I've got this variable, which I've called val, and it contains the value 3. I could make an x and a y. 1, y gets 2. If I execute those 2 lines of code, it added x and y to the list of values that I have stored. And so this allows you to set variables that sort of play important roles in your code. This allows for computing on unknown quantities, things like that. This unlocks a lot of the power of coding. So this is a very important operator. Say you've got a value and for whatever reason you don't know what it is, right? Pretend I didn't have this panel over here, but I knew that I had some variable x that I had been given, maybe by a collaborator, you can print a variable by just typing it into the line and hitting return. So if I just type X, it'll say that currently equals 1. If I do val, that currently equals 3. If I do something that doesn't exist, like var, oh, well, that's a function, so ignore that. VVV, right? It'll say error, object VVV not found, because I haven't created a variable that has that name. Print does the exact same thing as just typing the name of the variable and hitting enter. They're both just ways to display this object. Give me the content, show me what this object is. Variables are case sensitive. And now we get to the fun stuff. You can make them longer than length 1. So everything previously has been length 1. That's why we've got this 1 in square brackets. But if you wanted to, say, create a sequence of the numbers 1 to 6, you could do that with this type of construction, 1:6. And so seek 6. It's going to create a mySeq variable, and it contains the values 1 to 6. So the square bracket 1, it's always just talking about the closest thing to it. So this 1 is referring to this 1 here, saying this is the first element, but then there are 5 more elements. It's not enumerating all of them, but sometimes you'll have very, very long sequences. So if I do 1 to 100, it'll tell you this is the first element. And then when the text wraps around to the next line, it'll tell you this is the 14th element. And when it wraps around to the next line, it'll tell you this is the 27th element, and so on. And so these little square bracket numbers on the left are just a way to keep track of how long a particular sequence is. All of these are called vectors. So when you've got a sequence of numbers or of anything else, that's a vector. So mySeq is a vector of length 6. This 1 to 100 vector that I created down here is a vector of length 100. If you wanted to do, some other type of fancy stuff, you can manually create your own vectors with the C function. C is for concatenate. So if we did this, it would just, I'm not going to execute it. I'm jumping back and forth too much. It would concatenate these 3 numbers, 1.1, 3, and -5.7. And it would create a vector of length 3 that contains those 3 values. R norm is random normal. It's like the random uniform. Sorry, I showed earlier. If I do R norm 5, it's going to create 5 draws from a random normal distribution, and it'll put them into a vector called devs. So here, that's what they're doing, just generating 5 draws from a random normal distribution and then printing them out. And you can see it's 5 seemingly random numbers. I'm not going to bother talking about integers because they're basically the same as numerics, but characters. So you can do this with different types. Right now, we've only been working with numbers, but you could use characters, or you could use Booleans, true and false. There's also factors, which are a weird R specific thing, so I'm not going to talk too much about factors. But if I type just a string of text in double quotes, if I say hello, that's a valid R object. It's a character. And if I combine multiple of those, then what I get is a character vector. And this is exactly the same as the numeric vectors that we saw before, except the class is different, right? If I do class of mySeq it's going to say integer. If I say CV, class of CV is character. But other than that sort of metadata, it's the same basic structure. It's a vector. Booleans, like I said, are true and false values. These are another important type of data that you might be using, right? A lot of things can be written in these binary sort of true false values. It's important to note that it's only when it's in all caps. If I write true in lowercase, it's going to look for an object called true. And I haven't created one, so it says not found. If I do capital T, but then lowercase the rest, same thing. It's looking for an object called true. But if you do all caps, that's a special character. And that's recognized as being the Boolean true value. And same with false. That's a recognized object in R. And so, oh yeah, please. Yeah.
What does the bracket one indicate? It indicates there's just one of it.
Yeah, so actually everything that's being output is a vector. It's just a vector of length 1.
Okay.
Yeah. Really good question. Yeah, please feel free. I know I'm going super fast because I feel like there's so much to get through in 3 hours, but please do stop me if you're confused. The next important thing is indexing these vectors. Indices and subsets it's the same thing. How do I pull out specific values from a vector? And the answer is with square brackets. So if we've got something like mySeq, which is just the numbers 1 to 6, and for whatever reason, I want to pull out the first element, right? The way to do that is with a square bracket and then a 1. And that'll give just that first element. If I want to pull out elements 4 through 6, I can do that again with this colon notation that we saw before, meaning all of the integers between 4 and 6. I can do that, and it'll give me 4, 5, 6. Square bracket indexing is a powerful tool and pretty universal. Like, this works on a lot of our objects. A lot of data sets that we're going to see later are, in that nice rectangular format, and the subsetting is very similar. We'll get to that in a second. You can also index by a character vector, which is actually what I was doing before, right? Remember, 4:6 is itself a character vector, but it can be used as an index. And so if I instead wanted to pull out specific things, I could construct 1, 3, 5. I could construct my own vector and then use that to index another vector, and it would pull out elements 1, 3, and 5. If you use this minus sign, that's going to negate your index. It's going to pull out everything except those elements. And then another cool thing is that you can index by Boolean values. And so I'm going to switch to my character vector here because mySeq is a little long, but remember, that's just a character vector of length 3. If I index it by true, true, false, it'll give me the first 2 elements. This is a really powerful tool. It's not obvious as to why, but whenever you make comparisons in R, the result is a Boolean. So I didn't mention this when I was talking about math, but if I say, 1 less than 6, that's going to return true. And so by that similar token, if I say mySeq greater than 3, it's going to return a vector of Booleans and say for the first 3 elements, that's false. For the next 3 elements, that's true. And if I wanted to pull out the elements of my seq that are greater than 3, I could index it by that logical vector. And it would only pull out those elements that are greater than 3. Okay. They're going to work a little bit with this. I'm going to pause. Are there any questions? Yes.
Do apostrophe and quotation mark have difference? Like,
Apostrophe and quotation marks, so single quote versus double quote, both can be used to create character vectors. They interplay weirdly. So a character vector is going to respect whichever one you start with. So if I throw an apostrophe in here, it's actually going to be fine because this hello started with a double quote. So it's going to go till the next double quote. So I could throw as many apostrophes in here as I wanted, and it would still be fine.
and is it like using single quote for hello and then double quote for hi? Because
Yeah.
count as a
Yeah, that's totally fine. Yep. When it prints out, it's always going to print with double quotes for the most part. Okay. Taking a step back, the beauty of R is that it's free and it's open source. A lot of the other, this is why I think R is better than things like Stata, SPSS, and MATLAB, because you don't have to pay for it. R is free. And the fact that it's open source means that anybody can contribute. If you want to do something in MATLAB, you need MATLAB to make it available, or you need to write the code yourself. And that's really annoying. If somebody comes out with a cool stats method, I want to use that method, and I saw it in your paper, I can just usually install their R package and run it myself that afternoon. It's really nice, like being able to run anybody's code and generally having it be stable and have it run. So one of the main ways that code is distributed is through packages. And a lot of the packages that you're going to use come from CRAN. Just like R itself comes from CRAN. This is what a package page looks like. So this is the Gapminder package. You don't need to know about this package. It's not important. It holds a data set that Chris Pachorik likes to use for his examples. But this is what a CRAN package looks like. And it's super easy to install. All you have to do is go to R and say install.packages Gapminder in quotes. So I used single quotes that time because muscle memory, but double quotes, single quotes, doesn't matter. And if you do that and you're connected to the internet, it'll go to CRAN, it'll fetch that package, and it'll install. Yes.
You have to do it in the console, or can you do it in the file browser?
You could do it up here, and you'd still get the tab completion. So you'll notice that sometimes I just jump to the end of a thing. I forgot to mention tab completion, but it's great. You should use it. It doesn't run until I run it in the console. And so if I go here and hit Control Enter, then it runs in the console. Now it's just reinstalling it over and over again, just overwriting itself, which isn't really necessary. But once you have it installed, this is one of the tricky parts that bugs me a little bit. It's not available yet until you load it. And the way that you load a package is with library. Yeah. And this time you don't need quotes. This time you can use tab complete because now it's installed. Now it's on your computer. So R knows to look for it. And when I say library gapminder, it's going to basically look like it didn't do anything, but what it actually did is make that package available for me. And so now whatever code or whatever data is in that package is available to me in this R session. I think the main thing is just a data file, a data set called gapminder. Yeah. So if I reopen my environment, it's not even showing up because it's from a package. But basically, I now have an object available to me called gapminder. If I had done this before and just hit enter, it would have said object not found. But now it gives me a tibble, which is a type of table, of 1,704 observations by 6 variables. And so this wouldn't have been available to me before I did this library gapminder line of code. Quick plug, there's also Bioconductor. Not all packages are on CRAN. Some of them are on GitHub, and those are the ones that you can trust the least because that's just some random person's personal GitHub. But some of them are on Bioconductor, and these you can trust because Bioconductor, like CRAN, has a set of very thorough checks that they make every package go through in order to be accepted. And so if it's past those checks, you can be reasonably sure at least that the code is stable and runs on the particular types of data that it was designed for. If you want to install a Bioconductor package, use one that isn't mine. You can search for it, go to the page for that package, and there'll be a block of text under installation, and you can just copy this block of text and run it in your R session. Okay. Getting back to the slides. Indices and subsets. I'm gonna skip over that because we're running a little bit behind. I just want to mention, oh, okay. All right, the order here is weird. All right, I am going to talk about vectorized calculations because I did this once already. So I had that line earlier. I'm going to pull it up down here. I seek greater than 3. And remember that returned a vector of trues and falses. This is actually doing something pretty profound. And so this is a vectorized calculation. If you want to do the same operation on an entire vector, you can. And usually you can do that while just treating it like it's a single value, right? This is exactly the same syntax as if the first operator was a single value. I could do 1 greater than 3, I would get false, or I can do my seek greater than 3, and I would get a vector of trues and falses. This is very fast. This is what R is built to do. It's very fast. So anytime you have a chance to do calculations, anytime you need to do a lot of calculations, try to think if there's a way to do it in a vectorized manner. Because I could write a loop, right? I could write a for loop, or I could write an sapply, or I could write some sort of loop and use a lot of code to say, iterate over every object, every element of this vector, and for each of those elements, do some calculation. But most of the time, some of the time, a good chunk of the time, you can just treat that vector as if it's a single quantity and then do whatever operation to it you want. Times 3, but multiply them all by 3, or divided by 12. Divide them all by 12. This is going to be a lot faster. This is going to be a lot faster and less mental overhead, right? I had to write very little code for this. So be on the lookout for ways that you can exploit vectorized calculations. Okay. It's particularly useful for doing comparisons, which was why I started with that greater than 3 example. Okay. The other thing that goes very much hand in hand with what I was just saying is don't rewrite other people's code, because other people have probably spent a lot of time thinking about that code. If it's somebody else, if it's a package, just use the functions from that package. If it's something that can be done in base R, absolutely use the base R version of it, because R has been around for decades and the core functions have been optimized over and over and over and over again. They're so much faster than anything I could possibly write. So a good example is LM. LM is the linear models function. And all it does is fit a linear model. And if you Google, linear models, you can find the formula for doing that. It's like 4 matrix multiplications, right? X transpose X inverse, X transpose Y. 3 multiplications and an inverse. I could write code that does that, but I shouldn't. There's absolutely no reason why I should write that code, because the people who take care of R, the consortium behind R, has optimized this LM function. So it's so much faster than anything I could possibly write. The other thing that I want to point out here is I did something that I hadn't discussed yet. I typed $LM. Question mark is how you bring up the help documentation. And if I wasn't so zoomed in right now, you'd be able to see a little bit more of this. But this little panel on the bottom right is where the help documentation is going to pop up whenever you do that. So if I did, $LM, it would pull up the help page for LM. And this is going to explain very sort of high level how to use that function. You can also, if you really want to get into the nitty gritty, just type regular LM with no parentheses, and it'll show you the actual code. So this is the actual code of that function. Because R is fully open source, you can always look at the code to find out what any function is doing. I don't really know what this means. I'm not going to get into it, but if you want to know what a function is doing, it's totally possible. The help documentation is super, super valuable. And this is one of the reasons that I advocate for only using CRAN and bioconductor packages, or ROpenSci, if that ever comes up. They require that every function be documented. They require that every function made available through a particular package has to have a help page. And so you shouldn't ever encounter a situation where you're using an unfamiliar function and you have no way of getting more information about it. There should always be a help page. It's going to provide a little description at the top telling you what the function does. It's going to have some example usage, and then it's going to explain all the different arguments that you could potentially choose to put into this. So obviously for a linear model, you need data, right? You need an X and a Y. If you want to only run your linear model on a subset of that data, you can. If you want to do a weighted model where the observations have different weights, you can do that. If you want to use different methods under the hood, you can. There's a lot of different options for flavoring your linear model, and they're all explained in this help documentation. Just to pick another example, mean is the function for taking an average. I pull up $mean. It'll give me the help page for that function as well. Very similar, right? A brief description of the mean. It lets us know that we can do a trimmed mean if we want. It's an arithmetic mean, not a logarithmic, what's that called? Geometric mean. And there's, significantly fewer arguments this time because this is a a simpler function than linear model. But the help page should always be your first stop if you're confused about a particular function. Oh, we're running behind. Okay. Hist is the histogram function that is being demonstrated here. So I mentioned R norm earlier, random normal. In this line of code, all they're doing is generating 1,000 random normals and then plotting a histogram of those 1,000 values. And this is surprisingly quick because it's all vectorized. So I can do that. Not surprisingly, it produces something that looks relatively normal. This also demonstrates nested function calls, which is a very powerful tool. You can always treat an object and its output the same. So here we're treating this call to the function rnorm1000 as if it's already 1,000 random numbers. We haven't generated those yet. If I just type this line of code up here, those 1,000 random numbers are not actually generated until I run this code. But we can treat it as if it's already been run. We can treat it as if it's the actual output. So the more verbose and sort of pedantic way to write this would be x gets rnorm1000 and then histogram of x. But by nesting these function calls, we've sort of cut out the middleman. We didn't really need to save those 1,000 random values along the way. We talked about types. Okay, so now it's time to actually get into data frames. I'm going to treat data frames and matrices as pretty similar, but just know that a matrix is a two-dimensional array of values that all have the same type. And so remember, MySeq, these were all numeric, and CV, these were all characters. I could put these into a matrix in their own right, but I couldn't combine them into one matrix because one of them is numbers and one of them is characters. Those are two separate things. And so I couldn't even combine them into one vector. Or I could, but it would do something weird. It would convert one of them. So if I tried to do that, let's just see what that does. Yeah, it converted everything to a character. So notice my numbers 1 to 6 are now in quotes because that was sort of the only valid way to do it. There was no way to convert the characters to numbers. So it converted the numbers to characters, but now it just looks weird and it's clearly two different types of things. The problem with that is that when you're dealing with real world data, you'll often have variables that are different types, right? You might have age, which is a numeric, but you might have, country or state of residence, and that's a character. And you might have something else that's a true or false, like, an indicator for whether or not you have ever smoked. Things like that are going to come up a lot in real world data. And so the handy way for combining different types of data is generally a data frame. And this is what that looks like. Remember, we had this gapminder object before. It's a tibble, which is basically a fancy type of data frame. And it's going to look like this. It's a two-dimensional object. It's a rectangle of data. And each observation is a particular country in a particular year. Sorry. So all of these first 6 lines are all Afghanistan because they're listed alphabetically from the years 1952 to 1977. And it's just some basic information about each country and each year. The important things to know about this, one is indexing. So before we did indexing with the square bracket, we're still going to use the square bracket, but there's a difference now because this is a two-dimensional object. If I say dim gapminder, dim is the function for tell me how many dimensions there are. It's going to say 1704 by 6. I've got 1704 observations, and I've got 6 variables. That's the dimension of this data frame. If I try, if I want to pull out particular rows, it's going to look very similar, right? Sometimes you want to filter your observations because you've got outliers, or because you only want to work with a subset of the data. Maybe you only want to work with, African countries for a particular analysis. You can do that with the square brackets that we had before, Gapminder. So I'm just going to pull out rows 10 through 20. And the important thing here is I'm going to add a comma, because there are now 2 possible things that I could be indexing. I could be indexing either the rows or the columns. And so this comma is going to separate the row index from the column index. And so when I say I want rows 10 to 20, and then I don't specify anything for the columns, it's just going to give me all the columns. And so that's what I've got here. It's just, you can see we started in 1997, so this is clearly not the first 10 rows that we saw before. I pulled out rows 10 through 20 of this data frame, and it gave me all of the columns still. If I only wanted the first column, if I only wanted the first column, I could do that. And it would just give me that country column. For data frames, there's also a secondary way to subset the columns, and that's with the $sign. And this can be useful when you want to subset by the name of a column rather than the index of a column. So if I wanted to pull out the country, I could say Gapminder $sign country, and it would pull out the entire first column. And it did something smart here where it says omitted 704 entries. It only ever prints the first 1,000 of something, and that's to avoid some sort of mistake. If you've got a gigantic data set that has 100,000 entries and you accidentally print it out, you could be waiting for 5 minutes before it finally prints the whole thing. And so R is generally pretty smart about cutting it off at a certain point. This is just a vector now. If you use that $sign, this is just a vector. And now you can go back to subsetting it in a one-dimensional way. Not going to talk about lists. Yeah, data frames is where I wanted to get to, because data frames is where the USC materials start. And I think there's way too much stuff like that you should know before you get to data frames to just start with data frames. But it's not unfair to say that 90% of the time when you're working in R and you have a data set, the thing you're going to want to do is get that data set into R as a data frame. That's generally pretty easy. There's a whole interactive way to do that. This thing keeps getting in the way. I need to zoom out. The import dataset tab up here in the top right is going to allow you to import from different types of files that you might have on your computer. So the easiest one is a CSV, a comma separated values file. That's sort of a classic text-based table. But you can see there's a lot of different formats from which you can import data. And most of these will give you a data frame in R. So Excel is another super easy one. If you've got an Excel spreadsheet and you want to import it into R to do some nice plotting, you can absolutely do that. Most of this can be handled from this import dataset tab, so I'm not going to talk too much about how to actually do it. But again, if you're confused, Google it. That's most of what I do. Okay. And then I want to, why is this being weird? Okay. I want to talk for a minute about plotting. We've only got 4 minutes left. We started 5 minutes late, so I feel like we've got a little bit more than that, but if you need to leave, I understand. A lot of plotting in R is handled with ggplot2. That's a package. You need to install it the same way that we installed the other package with install.packages. I've already got it, but this is the tidyverse plotting function. This is I mentioned at the top that there's base R, and then within R, there's the tidyverse, which is its own dialect. ggplot2 is the tidyverse plotting package. And, for historical reasons, because it does certain things very well, ggplot2 really caught on. So a lot of people are going to use that. I still use base plot. So this histogram function that we used over here, that was a base plotting function, right? We didn't even have ggplot2 when we did that. And so there's a lot of powerful graphics that you have access to just within base R. But credit where credit is due, ggplot2 does do a lot of things very nicely in ways that would take a lot more code if you were to do them in base plot. Just to demonstrate that a little bit, I'm gonna not bother because we've already got our data set here. This is a facet plot. This is the type of thing that ggplot2 really excels at. This is, I think, the key reason why people would use ggplot2 over base plot is because if you want to facet a plot, it's showing the same two variables on the X and Y, but it's showing different subsets of the data in each of these subplots. That's extremely easy to do in ggplot. It's extremely hard to do, not extremely hard, but it's cumbersome in base R. And so ggplot2 is very good at things like this. Here they're actually plotting price of diamonds versus the weight of the diamond, and it's like colored by the color. I don't know. The two example data sets here are diamonds and cars, and so it just seemed very, like if we threw in housing, it would be the trifecta of things I can't afford. Yeah, I want to get to the actual plotting. This is how it generally works. There's a function called ggplot, and it takes a data set. So this is the paradigm of ggplot, is that everything starts from a data frame. And since I just said, most of the time you're going to be taking data from the outside world and importing it to R as a data frame, this is a very reasonable starting place. The problem is that then there's this weird syntax of a plus sign, but it's not actually doing addition. This is weird syntax that is very specific to ggplot, and you won't see anywhere else, as far as I know. But essentially, there's a whole family of these geom functions, and that's going to determine what type of plot are we building. Are we building a histogram, a scatter plot, a box plot, a pie chart, whatever? And then the mapping is going to tell us which of the variables from my data go with which components of that chart, right? What do I want on the x-axis? What do I want on the y-axis? And so very quickly, here they just show, I apologize, it's hard to pick a correct zooming. This diamonds is a data frame, just like Gapminder. If you just call ggplot on a data frame, it's not going to give you anything. It doesn't know what to do with that data set. If you call it on that data set and then say, I want to scatter plot, it's going to give you an error because it doesn't know what you want on the X and Y axis. This data set has 4 or 5 different columns. And so there's no way of knowing which of those columns should be the X and which of those columns should be the Y. And so the fully correct way to just do a scatter plot with 2 columns from a data frame is this. You have to call ggplot on the data frame and then add this geom point because you want a scatter plot, and then create a mapping with the aesthetic function and say on the x-axis, I want caret, on the y-axis, I want price, and then it has all the information that it needs to go ahead and actually produce a plot like this. This type of plot would be much easier in baseplot. I'm just going to throw that out there. Like baseplot would be a lot easier because it can just take 2 vectors and plot them. But there is a sort of nice philosophical coherence to keeping the data together. And that can save you time down the road, because if you're constantly pulling out parts of a data set and using them for a little bit and then going back to the original and pulling out different parts, it's very easy to get lost. It's very easy to lose track of which parts go where and which parts have been subset and which parts haven't. So I do understand why ggplot is built this way. It's to keep the data as the focus. The data frame itself is the focus. It's just, it requires a little extra code to actually get the plot that you want out at the end. That said, super powerful. You can do a lot of things with ggplot. Add color. You can, like I said, do the facet plots, which are one of the big, selling points here. And here they're just showing how to specify all of the different labels. This is something I've had to Google literally every time. Like whenever I need to change the x-axis label, it's always, how do I do this again? And the nice thing, again, because R is open source and anybody can contribute, lots of people have made extensions to ggplot2 that can do things like word clouds. You can animate stuff. You can make these nice ridges plots. I've heard lots of different names for these, but stacked density plots. Yeah, that's where I'm going to leave it today. ggplot2 is really, I think, the reason this is in the first lecture is because it's the carrot. It's that first hit of actual real coding with tangible outputs that look cool. And so I think this is how a lot of people get hooked on R generally and the tidyverse specifically. And it's a really great entry point. Once you get the hang of it, it's really not that hard to create very nice looking, very attractive plots. All right. I'm happy to answer questions. I see that somebody just entered, so we might not have this room anymore. But I hope to see you all tomorrow.